If you watched my video about send protocol, you noticed that in Picoscope we selected send fast to decode that protocol, but there is also send slow. What is it and what can it be used for? Send slow is a protocol that is hidden inside the regular send protocol. And a good description of that can be found in a tutorial by Integrated Device Technologies with the link, as usual, in the description to this video. Recall that a typical send packet consists of a synchronization pulse, a status nibble, 4 bits, and then 24 bit of data, and then finally 4 bit of checksum, CRC. If we receive many packets one after another, what we can do is we can take a status nibble, take its two highest bits, here it's bits 2 and 3, and line them up in a table like this. From the first packet we'll take those bits 3 and 2. From the second packet that we received, we put bits 3 and 2, and so on for 16 packets. And this will form our slow send message. What it will have is the start of the message. It will be denoted by 1 for bit 3, and all the rest will be zeros. Values for bit 2 will give us the following. The first 4 values will give us a message ID, then there will be 8 bits of data, and finally a 4-bit CRC code. And this is our slow message that takes 16 regular send packets to be transmitted. What can we use the slow channel for? Well, we can use it for the values that do not change fast over time, such as temperature or atmospheric pressure. It can also be used to transmit the serial number of the sensor, or even some sort of a rolling code that is known only to the sensor and the receiving microcontroller. And this would prevent unauthorized sensors from being connected to the microcontroller, because it would be able to detect that they use an incorrect code and reject them. Depending on your worldview, it's either an exciting or a terrifying possibility, because if such thing is implemented, there would be no aftermarket sensors without the manufacturer providing the algorithm for the rolling code. So on the one hand, there wouldn't be substandard sensors installed instead of the good ones, but on the other hand, the manufacturer would have complete control over the pricing and the distribution. Okay, let's address those issues later on, but now let's take a look how the slow channel looks on the Picoscope. For that, we would need a sensor that transmits both fast and slow send data. For example, a Bosch HFM8 massive flow sensor, which, as we see from the description, supports digital signal transmission by a send interface, but it costs too much to play with it, so I don't have it. Instead, I'm going to program a small microcontroller at Tiny85 to transmit both fast and slow send packets and see what happens on the Picoscope. So let's quickly describe what we are going to do with the MCU. Here is a circuit. A tiny 85 is usually powered up anywhere from 3.3 to 5 volts. It has 3 ADC channels, A1, A2 and A3, and we are going to use them all to collect analog data and then convert it into the digital send packets and send them out on pin 0 that is connected to channel B. We are going to do a little bit of smoothing of the signal and then feed it to channel A, which we are going to use for decoding. So what I did with the ADC channels, A1 is just connected to 5 volts, and so we are going to see that measurement there. A2 and A3 are connected to a potentiometer. It's set about 2/3 of the way, so we will see that those values as well. The values from A1 I'm going to transmit using the fast channel, channel 1. A2 I'm going to transmit on the channel 2 of fast channel, but A3 is going to go to the slow channel, and it is 10 bits, so I will split it into two 8-bit chunks, and I'm going to transmit them using the message ID 0 and 1. Interestingly, this MCU also internally measures voltage and its own temperature, so we can also transmit them using the send slow protocol on IDs 2 and 3 and 4 and 5. Once we get to the values in the Picoscope, it will be obvious how to interpret those values, but now we can see how it looks on the breadboard. So this little chip, a few resistors, capacitor, and the Picoscope probes. That's pretty much it. Interestingly, for some unknown reason, I used 3.3 volts instead of 5 volts to power this processor, but it's not a big deal. On the Picoscope, instead of 5 volts, we are going to see 3.3 volts. That will be the only difference. Okay, without further ado, let's switch to the Picoscope and see what we have there. And what we have in the Picoscope is the following. I have collected data coming from the MCU in the streaming mode of the Picoscope, so the sample rate is 1 megasamples per second. This corresponds to setting the time base to 200 milliseconds per division and making the number of collected samples big. Here I'm using 10 megasamples. If you need any clarifications of what the streaming mode is for the Picoscope, please look for my video on this topic, and I will include the link into the description of this video. Now, what we see here is that the Picoscope collected a number of packets transmitted, and at this zoom level it's just one big blur, so we will have to zoom in a lot to see what's going on inside. So let's do just that. So at this zoom level we already see that there are individual sent packets being transmitted, and we can focus on, let's say, 2 of them, and observe that indeed they are sent packets with the synchronization pulse and the nibbles transmitted, just as we've seen in one of the previous videos. The Picoscope thinks that the sample rate of 1 megasamples per second is kind of slow to decode the sent data, and it's kind of, yes, at the boundary. It's still able to decode all the data correctly, so we probably shouldn't worry about it too much, though it can present issues for some other situation when there is more noise on the line. But here it's not an issue. We can see that each sent packet is transmitted correctly and it passes the checksum. We can see what the data is. It is easy to interpret the fast data. 3FF is the maximum value that fits in a 10-bit number. This MCU has a 10-bit ADC, so this is the ADC input connected to the power supply, and that's exactly what we did with channel A1. 294 is a value that is about 2/3 of the maximum that fits into 10 bits. That's the value coming from the potentiometer. And we can see that in all the packets the checksum passes, so everything is fine. One interesting thing that we see is the message start is checked when the status is equal to 8. And this is not a coincidence. This is our bit number 3, as we've discussed for the slow channel, being equal to 1. So even in the fast serial decoding data, we see that something interesting happens in the slow channel. If we add a slow channel a decoding in Picoscope, here is an example how to do that. Here we will see some other data appearing, and it takes 16 packets to give us one message. So we'll have to zoom out somewhat to look at the whole packet. So after we zoom out all this train of packets, we can see what we have in the slow channel. So we have a packet 1, message ID is 0 and the data is 0904. CRC is passed. So it's a good slow packet. Then packet 2 has message ID 01 with the data 0002, and so on. We have in total 6 slow packets, and we can see them in the table as well. We have a tab for the slow channel here. Now let's examine the slow data more closely. Let's go to the serial decoding table and switch to the Send Slow tab, where we will find 6 packets with message IDs from 0 to 5. Checksum passes for all of them, which is good news for us. And the data is for message ID 0, it's 94. For message ID 01, it's 2. Remember, this is the message IDs for ADC channel 3, and this represents the low byte, and this is represents the high byte for it. So the number that's reported is 294. Does it remind us of something? Yes, it does. We've seen this number already in the fast channel right here, 294. This was for ADC channel 2, and this is no surprise because both channels 2 and 3 were connected to the same potentiometer, so they should give similar, or in this case exactly the same values. So we do have the correct data transmitted. Interestingly, the Picoscope also has the column called MAF data field, so mass airflow data field. It looks like they took some mass airflow sensor and just deciphered what exactly was transmitting, and it has a few messages where it transmits high byte and low byte of air temperature, humidity, barometric pressure. So I'm not sure how different MAFs are, but it's quite possible that they are fairly standardized in what kind of data they transmit, and maybe it simplifies the process of deciphering the data a lot, because you would be able to see what the air temperature is, what the humidity is, and so on. But in our case, we are obviously not transmitting the same data because we are using our own sensor. Going to messages 2 and 3, we have 148. 148, which is in decimal is 330. This is supposed to be representing the voltage supply for the MCU. And how it's getting this voltage? It has an internal reference, 1.1 volts, and it sends it to the ADC channel that receives power supply from approximately 3.3 volts in our case, and the digital result is being reported here as 330 out of total 1023. So to figure out what the power supply voltage is, we need to take 1.1 volts multiply by 1023 and then divide by the value that we observe, 330, and we are getting 3.4 volts, which is close enough. I'm not sure how precise this value is, but it's close enough to 3.3 that we see as our power supply. Then 4 and 5 are giving us value 11A, and this is supposed to be the temperature. 11A in decimal is 282, and for this chip, to get the temperature in Celsius, you have to subtract a value that is approximately 260. So this means that the temperature of the chip at the time of the measurement was 22 Celsius, which is pretty much what was in the room. Maybe a little bit warmer because the chip gets a little bit warm by working, consuming some current. So again, we are able to interpret this value. So here we go. We have the serial decoding working for both send fast and send slow channels, and we are able to confirm that the checksum is okay, and it's not very hard to interpret the data once we have understanding of what different fields mean. Okay, now after this lengthy video, you know everything you need to know to diagnose a send communication. But for the electronic enthusiasts among us, they might still have a question about whether they can use send protocol in their own electronic projects. And this is a topic that I'm going to touch on in future videos, so stay tuned.